Hey, analysis. Before we get started in this video the normal way, where we go over what we're going to do, I have an integral I want you to complete, and it is as follows. The integral from 1 to 5 of 1 over x minus 2 dx. Go ahead and solve this. Alright, if you're like me, not really intimidated by this, cool. We got natural log, the absolute value of x minus 2. Evaluated from 1 to 5. Put those things in, we get ln 3 minus ln negative 1. We get ln 3 minus ln 1. Our ln 1 is just 0, so our final answer is the natural log of 3. Alright, that wasn't that bad. Today's lesson is going to be easy. Well, we have broken the fundamental theorem of calculus, and think about why. Why is this not the answer? The fundamental theorem of calculus, what permits us to anti-differentiate this, requires a condition. And that condition is the function must be contiguous. The function must be continuous. And on our interval 1 to 5, 1 over x minus 2, that is not continuous. We have a discontinuity at 2. 2 is contained in the interval 1 to 5. Up until now, every single definite integral that we've had you evaluate has been continuous on the interval that we give you. We have been good teachers. We have always given you doable problems. This problem is not doable with the tools that you have right now. However, this problem is doable after today's lesson. With that said, let's begin today's lesson. Today's lesson is improper. Improper. Let me fix that. Come on, eraser. Improper integrals. What we were just looking at was an improper integral. This is section 8.8. And in this video, we are going to look at two types. Type 1 and type 2. There are two types of improper integrals that we are going to be looking at. Additionally, we're going to be doing lots of examples. I hope that helps. And then we will finish this lesson with one of my favorite math problems of all time. Gabriel's horn. I'm very excited for that, and I hope you are too. With that said, let's go ahead and look at our first type of improper integrals. Here it is. Here's your definition. This is different than the problem that we did at the very, very beginning. Take a moment to read this. Alright, hopefully you were unable to hear my dishwasher in the background, but here is your definition, the definition of an improper integral. If the integral from a to t of f of x dx exists for every number t greater than a, then provided this limit exists as a finite number, a to infinity of f of x dx is equal to the limit as t goes to infinity of a to t f of x dx. Replacing infinity with t and then constructing a limit and letting t go to infinity. Right, likewise, we can do it on the other side. Right, we can come from negative infinity towards b if the integral from t to b of f of x dx exists for every number t less than b, right, as long as we have this existence, then provided this limit exists, negative infinity to b of f of x dx is equal to the limit as t goes to negative infinity of t to b f of x dx. We are replacing the infinity in the bounds of these integrals with t and then letting t go to infinity. Right? If the limit exists and is a finite number, then we say that the integral converges towards that number. Right? The improper integrals a to infinity and negative infinity to b are called convergent if the limit exists. If the limit does not exist, it's trash, it's garbage, we throw it away. It is divergent, the limit does not exist. All right, that is my big tip for you today. If the limit does not exist, then the problem is trash, regardless of what your heart, your soul, your intuition says. If the limit does not exist, if it's infinity, if it's negative infinity, if it's divergent, the entire problem crumbles to the floor. Keep that in mind. There is one more subsection of type number 1, and it is if both negative infinity to a of f of x dx and a to infinity of f of x dx are convergent, then we can take the integral from negative infinity to infinity of f of x. And that is equal to negative infinity to a, and then a to infinity. A is some arbitrary point between negative infinity and infinity. As long as these exist, as long as they're convergent, then this integral will work. I want to provide some more context before moving on as well, why this makes sense in the slightest. And we're going to take a stroll back to pre-calc with sequences in series. So in pre-calc, you had the sequence 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus ... And this sequence converged. There was no number of which this sequence was getting closer and closer and closer to. Right? If you were to arbitrarily give me a number, I could surpass it eventually with this sequence. With this series, with this infinite series, 1 plus 2 plus 3. Our sequence would be a list of numbers. I've made an inaccuracy here. We're adding up an infinite list of numbers. That's a series. But this ultimately diverged. If I said, when is this going to get past 1 million? It would eventually get past 1 million. Right? But you also had this series. And this series converged. This is getting closer and closer and closer to 2. Right? This is equal to, based on the definition that we've used in the past, this is equal to 2. This thing diverges. This thing down here converges to the number 2. This second infinite sum will never get past the number 2. And that's what we mean by it diverges to 2. I mean, there's a little bit more to it than that. Right? This will also never get past the number 3. It doesn't mean it converges to 3. Right? But the limit of this series, as the series goes out further and further, is 2. Why is it that the first one diverges and the second one converges? Well, there's math that tells us that it goes to 2. But also the bigger idea is that it's all about the rate of how something decreases. Right? My sequential numbers are decreasing at a faster rate in the second example than the first example. And there's something that happens in between decreasing in a harmonic series and decreasing in a geometric series. In today's examples, we are going to be looking at how something decreases. How fast does it decrease? And our goal is to figure out if it converges or if it diverges. If it diverges, we're done. It's almost like if you like to do a little amount of work, then you're done. You're happy. Problem is, divergent things are useless. Well, not useless, but divergent things are not as useful as convergent things. So the convergent is obviously going to have a little bit more work because we're going to have to figure out what it converges to. But it is nice when a integral converges because then we have a value that we can use. Here is my first example for you guys. The integral from 4 to infinity of e to the x dx. You could think about this potentially and determine whether it's convergent or divergent just by looking at it. Right? When we were talking earlier, we were talking about things that were decreasing. Think about why this might, why this might decrease or increase. Why we might be able to just determine if it diverges or converges immediately. But let's actually do the problem in a formal way to solidify our understanding of these definitions of improper integrals. So, when doing a problem that involves an improper integral, it's imperative that you use proper notation. So I'm going to write an equal sign. And what I write on the right side of this equal sign must be equal to the left side. So please don't be lazy in your notation. Right, I'm going to use the definition. 4 to infinity of e to the x dx is equal to the limit as t approaches infinity of the integral of 4 to t of e to the x dx. Right, these two things are equal by definition. Right, please don't just like write 4 to t. Don't skip this line. This is step one. Step one is it improper? Step two, write it as a limit. And once you've done that, just evaluate. Like normal. All right, but please don't neglect this step. All right, let's proceed. The limit, I'm just going to rewrite that, of the integral from 4 to t, e to the x dx. All right, the antiderivative of e to the x is e to the x, so we have the limit as t goes to infinity of e to the x evaluated at 4t, and then we subtract 4. And then we have the limit as t goes to infinity of e to the t minus e to the 4. And this is a mere mortal. Infinity wins infinitus once again. We diverge here. All right, but go back to the original question that I was asking. Why must this diverge just by thinking about it? Let's draw e to the x. Here's e to the x. We're going from 4 to infinity. Right? We're trying to find this area. And if we start thinking about rectangles, Riemann sums, right, we're going to be adding, let's say 1 plus 2 plus 3 plus 4 plus dot, dot, dot. These numbers are arbitrary. Right? We're going to be adding larger and larger numbers. This series obviously diverges. Right? In order for a series to converge, these numbers need to be decreasing. We are looking for decreasing functions. Of course, there are some exceptions to the rule, and we'll see that when we look at the part 2 definition of improper integrals. But in these part 1 integrals, as we go to infinity or as we go to negative infinity, or well, actually as we go to negative infinity, if we are decreasing, then the things that we're adding up are going to be getting bigger and bigger and bigger. We're looking for these rectangles that we're taking as we go to our infinite bound to be decreasing. All right, here is your next example. The integral from 5 to infinity, type 1, of 1 over 2x minus 7 cubed dx. All right, let's take some advice from our past self. Let's make sure that we are not discontinuous between 5 and infinity. Type 1 requires that we're continuous between 5 and infinity. All right, and our discontinuity point is at 7 halves, 3.5, which is to the left of 5. So we are good. We are good. Step 1, is it improper? If it wasn't, we would just do it the normal way. But this is improper because we have to add infinity. Step 2, write it as a limit. Write it as a limit. This is equal to the limit as t goes to infinity of 5 to t of 1 over 2x minus 7 cubed dx. All right, let's integrate as normal. That's step 3. We have the limit. Now we just have to carry this limit with us as we go. 5 to t of, I like to rewrite it as 2x minus 7 to the negative 3. But we're all now integration experts now that the integration unit is over. So do this however you like. Limit t goes to infinity of 5 to t. Actually, no, it's time to integrate. Get rid of that. We're going to be integrating from 5 to t. Raise this to the negative 2, divide by negative 2. But then we also have that 2 on the inside, bring that on the outside. Oops, I meant to bring that 2 on the outside in the denominator. Boom. You know what, I'm second guessing myself. That's totally natural, normal. I'm going to go ahead and just double check that the derivative of 2x minus 7 to the negative 2 divided by negative 4 gives me what I had in my integrand. So I bring that negative 2 down. Negative 4 in the denominator, 2x minus negative 7, and that's going to become a negative 3. Then I need to use the chain rule, so that 2 is going to pop out. And boom, 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 2x minus 7 to the negative 3. Perfect. All right, that is the correct. And you know what? While I'm down here, I'm going to turn that into a negative 4. I'm happy. All right, let's proceed. All right, we're evaluating this at t, then subtracting it, evaluated at 5. The limit. Do not drop the limit of 2t minus 7 to the negative 2 over negative 4 minus, what's that going to be? 10 minus 7, 3 to the negative 2 over negative 4. Let me go ahead and take this to the next page. Awesome. And let's see, I'm going to rewrite this one last time because now that I've got everything evaluated, I want my negative power in the denominator. So we have 1 over negative 4 times 2t minus 7 to the square minus, that's going to be 1 over 9 times 4, 1 over plus 36. All right, as t goes to infinity, this thing blows up. And we're going to be getting closer and closer to 0 from the negative side, but that's not something that we particularly care about. This expression goes to 0, and our final answer is, as the limit, as t goes to infinity, 1 over 36. This is I'm going to go ahead and change my color real quick. This is a 1 over x cubed graph, a transformation on a 1 over x cubed graph. So just for the sake of drawing a little picture, I'm going to have some stuff down here. Oh, then we're going to have this bit. We are decreasing, not the smoothest thing in the world. Right, and then the discontinuity, I think we established, was at 7 halves. But we are going from 5 to infinity. And so we are looking at this area. And this area converges to 1 over 36. Wonderful. Right? This obviously is not drawn to scale at all, but our integral converges. Wonderful. Here's another problem. 5 to infinity of 1 over 2x minus 7 to the 5th dx. And before you go and solve this, I'm not asking you to solve this one. I'm simply asking you, does it diverge or converge? And take a second to think. Let me spell converge right. Take a second to think. why this might converge or diverge. All right, this one definitely converges because this graph is less than the previous graph. Let me go back to my green. If I give myself that previous graph from 5 to infinity, this graph to the fifth, this is less. Let's just go ahead and say it's like this. All right, we're going to use this rule a lot in the coming weeks, in the coming months. All right, a comparison test of sorts. We know that 1 over 2x minus 7 to the fifth is going to converge on these bounds because it is less than 1 over 2x minus 7 to the third. Right, so if the question is asking, does it converge, and you know that something larger than it converges, then you can simply say that it converges. Right? What it converges to, we're going to need to evaluate to establish that, but that's not what I'm asking here. I was just simply asking you, does it diverge or does it converge? And this converges. All right, this was our second example. Let me give you a third one. How about 5 to the infinity of 1 over 2x minus 7 dx? Right. Can we determine whether it converges or diverges? Just by looking at it? Right. With what we've done, we cannot determine whether it converges or diverges. Right. This is larger than the previous graph. So if we knew that 1 over 2x minus 7 to the third diverged, then this being larger would tell us that it must diverge. Right, but because we know that the thing that's smaller than it converges, this is telling us nothing about a graph that's larger than our first example. So we need to actually evaluate this one. So let's go ahead and do it. This one won't be too bad. It's a little bit easier of an integral. All right, step 1. Is it an improper integral? Yes. So we need to rewrite it as a limit. Step 2. T goes to infinity. I was about to write x, if you could tell. Of 5 to the t of 1 over 2x minus 7 dx. Mr. Schwartz and I very much care that you're being careful about your notation. All right. This one's going to be a little bit more simple. We're going to have a limit as t goes to infinity of the natural log of 2x minus 7 dx over 2. And if I quickly do some differentiating, I'm going to get 1 over 2x minus 7. The 2 is going to pop out, cancel with that 2. We are good. I'm a little bit more comfortable with this one. Cool. That dx should not be there. That's my bad. We are evaluating this from 5 to t. Right, so this is going to be the limit as t goes to infinity of the natural log of 2t minus 7 over 2 minus ln 3, and I'm going to get rid of those absolute values, over 2. And you know what? We're going from 5 to infinity, so I can actually get rid of these ones as well. Awesome. We're dealing with positive values. All right, the limit of this thing. All right, that is a number, so let's not worry about it. This thing goes to infinity as t goes to infinity. Oh no, this thing diverges. It's similar to the 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 situation. ... Right? We are diverging here. Problem number 4. This is a simply does it converge or does it diverge problem. 5 to infinity of 1 over 2x minus 7 to the 1/2 dx. Can we determine whether this converges or diverges? And we can. We can this time. We just established that 1 over 2x minus 7, 1 over 2x minus 7, 1 over 2x minus 7 diverges. And this graph, because of the power being less, is going to be larger than. So if this is our 0.5, if the white curve here diverges, then the blue curve must also diverge. It is larger than the white curve. If the area under this is infinite, then make sure my colors are right. If the area under the white curve is infinite, then the area under the blue curve will most also definitely be infinite. This problem diverges. In example number 2, we might have wanted to know what the area under that curve was, but we didn't. We just established that it converged. But here, it doesn't matter if we want to know what the area under the curve is because it most definitely diverges. It's an infinite area. All right, we're still working with type 1 of improper integrals. I have not given you the definition of the second type. But I got one last example for you before we move on to the second type, and that is that type C. Right, when your bounds are both infinite. 1 over 1 plus x squared dx. Let's evaluate this thing. All right, step 1, is it improper? And this one is improper. And we're continuous everywhere between negative infinity and infinity. So if we choose a point in between negative infinity and infinity, our two broken up improper integrals will be valid in terms of solving. So let's split this thing up into two limits. So we have that this is equal to the limit as t goes to negative infinity, t to, well, so let me graph this real quick. This is the Witch of Ignesi. It's going to look a little bit like this. Where might we want to, this is continuous, where might we want to split this up? All right, if your heart says, let's split this up at 0 and use symmetry, you would be mistaken. Right? 0 is not halfway between infinity and negative infinity. Negative infinity and infinity are not numbers. There is no quantifiable middle point between negative infinity and infinity. So if you were tempted to go from negative infinity to 0 and 0 to infinity and equate these two integrals, you would be incorrect. You cannot do that. You cannot do that when you're dealing with negative infinity. Infinity is way more complicated than that. So 0 is a reasonable place to pick, but it is not directly in between negative infinity and infinity. So 0 is just as arbitrary as 42. Let's do 42, meaning of the life, the universe, and everything. So we're going to go from t to 42 of 1 over 1 plus x squared dx plus the limit as t goes to infinity of 42 to t of 1 over 1 plus x squared dx. Right, 0 is, this is why I chose this problem, is so that you are tempted to use 0 and use symmetry and then just do 2 times the first integral. All right, but 0 is not halfway between negative infinity and infinity. Right, so let's go ahead and evaluate this now. The limit as t goes to negative infinity. All right, we live for integrals like this because this is just an arctan. All right, we're evaluating this arctan of x, evaluated from t to 42, plus the limit t goes to infinity of, and we evaluate arctan of x from 42 to t. Cool, let's go ahead and take this to the next page. Awesome. Go hide that other stuff. No. There we go. Get rid of that. Cool, let's evaluate. All right, so the limit as t goes to infinity, negative infinity, sorry, of the arctan of 42 minus the arctan of t, and then plus the limit as t goes to infinity. All right, I'm writing this every single time because the equal sign has a meaning, and we must respect that meaning. Respect the equals. Arctan of t minus arctan of 42. Cool, so we can evaluate these things. The limit as t goes to infinity, negative infinity, I keep doing that, of arctan of 42, that's just the arctan of 42. And as the limit as t goes to negative infinity of the arctan of t, well, I know what the arctan of t looks like. I'm going to go ahead and draw that in my margins up here. Arctan of t, it looks like this, with horizontal asymptotes of negative pi over 2 and pi over 2. Okay, so as I go to negative infinity, arctan is going to negative pi over 2. And so I'm subtracting that, I'm going to get a positive one. All right, the limit as t goes to, let me just go ahead and get rid of that limit. As t goes to infinity of arctan, that is pi over 2. And the limit as t goes to infinity of arctan of 42 is just arctan of 42. All right, these things cancel. Negative pi over 2 times negative pi over 2 plus pi over 2, that is pi. Our final answer here is pi. And notice that it wouldn't have mattered if we chose 0, or if we chose 43, or if we chose 47, or if we chose 1,621, or negative 1,621. We would have gotten arctan of all those numbers, the opposite of that number, and they would have canceled. And the only thing that mattered here was that arctan of t, and we would have gotten pi, regardless of how we chose to do this. The area under this curve, let me go back to my attempt at drawing the curve right here. The area under this curve is pi, while the bounds are infinite. The area under this curve approaches the value pi, and it will get infinitely close to pi. It'll get, in fact, as close to pi as you want without surpassing it. All right, so we say, because the limit goes to pi, that the area under this curve is pi units squared. All right, it is time for the second type of improper integral. The second type is what we did at the very beginning of this lesson. Here it is, our second definition of improper integrals, type 2. If f is continuous on a inclusive to b non-inclusive, and we are discontinuous at b, then we redefine a to b as the limit as t goes to b from the left-hand side of a to t, f of x dx. If f is continuous on a to b and is discontinuous at a, then we redefine the limit as t to b as we approach a from the right-hand side. If these limits exist, we call it convergent, and if they do not, we call it divergent. We have a part C for this definition as well, and this is the one that we did at the beginning of the video. If f has a discontinuity at c in between our bounds a and b, and both a to c and c to b are convergent, then we can define the integral from a to b where there's a discontinuity between them at that value c to be a to c and then c to b. Right, but it is granted that those are convergent. If either are divergent, this is trash. We throw it away. The final answer is divergent. Let's do that original example. Ooh, I'm still in blue. Look at that. Well, we'll just do it in blue. All right, we had 1 to 5 of 1 over x minus 2 dx. All right, we have a discontinuity at 2. So let's go ahead and rewrite this as the limit as t goes to 2 from the left-hand side of 1 to t of 1 over x minus 2 dx plus the limit as t goes to 2 from the right-hand side of t to 5, 1 over x minus 2 dx. All right, we want to evaluate this thing. All right, so this is going to be ln x minus 2 evaluated from 1 to t. Let me not forget my limit. And then this is going to be the limit as t goes to 2 from the right-hand side of ln x minus 2 evaluated from at t and at 5. All right, I hope you guys don't mind. I think I can fit this final line here on the bottom to save the trouble of going to a new page. We have ln, so the limit as t goes to 2 from the negative side of ln t minus 2 minus ln 1, which is just 0. And then over here we have the limit as t goes to 2 from the positive side of ln t minus 2, or no, sorry, ln 5 minus ln t minus 2. Cool. All right, but as we get closer and closer to 2, this side is just straight up undefined. Oh, actually, no, it's not, because we have these absolute values. Never mind. But this is getting closer and closer to 0 from the positive side, so that thing is shooting to negative infinity. All right, this is divergent. Right? While this is going to also be divergent, I don't care, because the second one of my limits is divergent, then my final answer is divergent. Divergent. My final answer is divergent. The second one of my two limits is divergent. I don't care if the other one is finite. And the answer being divergent kind of makes sense to me, because if I look at the 1 over x graph, at the point of discontinuity, right, if I rotate this 90 degrees, I'm basically dealing with the same thing over here. We talked about how this was divergent. So this symmetric spot is also going to be divergent. Right? The area between the y-axis and my curve here is going to be, in a way, the same as the area between the curve and the x-axis. So if I'm approaching a point of discontinuity with the graph 1 over x, it's going to be that same idea of 1 plus 1/2 plus 1/3 plus ... and how that's divergent. When I think about improper integrals, I'm constantly thinking about 1 plus 1/2 plus 1/3 plus 1/4 and how that's divergent, and 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 and how that's convergent. Right, those two concepts help me make sense of these definitions and my final answers being divergent or convergent. Okay, let's do an example. Let me get out of the screen and go back to white. Let's do an example where it is not divergent, because that'd be nice to get both. So 2 to 4, 1 over the square root of 12 minus 3x. All right, our point of discontinuity is 4. It's one of our bounds. This is 2, not a 0. It's 4, one of our bounds. So this is type, I believe, type A for part 2. But regardless, we do not need to split this up into 2 integrals. We can just do a single limit. We are doing the limit as t goes to 4 from the negative side of 2 to t, 1 over the square root of 12 minus 3x dx. Let me add that here too. Once you've rewritten it as a limit, life is pretty good. It's pretty simple, pretty straightforward. Let's see. The integral of this, I'm going to rewrite this as, I'm just going to do it over here as some scratch work. Square root, and instead of writing the square root, I'm going to write 12 minus 3x to the negative 1/2. That's how I like to do it. Raise that up, divide by what the new power is. That's going to be 1/2, so I'm going to have a 2. 12 minus 3x to the 1/2, and then I need to divide by what's inside. That's going to be a negative 3. Sweet. I believe this is correct. It's always nice to just check my answer, though. All right, this is going to be the limit as t goes to 4 from the left-hand side of negative 2/3 times 12 minus 3t to the 1/2 minus plugging in 2 to this thing. So 12 minus 6. That's going to be 6. 6 to the 1/2, so plus 2/3 times 6 to the 1/2. Ooh, that's nice. As t gets closer and closer to 4, this term, that's going to 0. This is going to 0. And then this is just going to 2/3 times 6 to the 1/2. So I believe my final answer is 2 times the square root of 6 over 3. Sweet. We got a final answer here. While this graph right here has a vertical asymptote at 4, the area under the curve has an upper bound limit of 2√6 over 3. All right, as you take smaller and smaller intervals and you make this area more and more refined, you're getting closer and closer, as close as you want, to 2√6 over 3. So we go ahead and we say that the area under the curve is 2√6 over 3. We'll never surpass this number. Oddly satisfying, no? All right, I have one final example for you, and it's like my favorite example ever. Example number 8. So, before we begin, let's draw a picture. Make that line a little bit more straight. That's satisfying. All right, we are graphing the function 1 over x from 1 to infinity. Let me write that a little bit better. From 1 to infinity. So 1 over x, that's going to be 1. And then at 2, it's going to be 1/2. At 3, it's going to be 1/3. And so on and so forth. Oops. Let me just go ahead and... The next thing I want you to do is I want you to take this curve from 1 to infinity, 1 over x, and I want you to revolve it around the x-axis. Add another one there just for depth. This curve is called Gabriel's horn. It's also referred to as Torricelli's trumpet. You can pick and choose which one you call it. I'm going to call it Gabriel's horn because that's what I know it to be. We have here an infinitely long horn, an infinitely long trumpet. And what I want you to do is I want you to find the surface area of this trumpet. All right, we know how to do this. It's going to be, the surface area is going to be 2 pi, the integral from 1 to infinity. All right, this is going to be the type of problem that we've been doing all video of the radius, which is just y. What is y here? Y is 1 over x times the square root of, we are dealing in terms of x, so it's just going to be 1 plus the derivative, and I'm going to do this in steps, squared dx. All right, it's fitting to finish the quarter with what we started the quarter with. All right, the derivative of 1 over x, that is just going to be, well, let me write everything again. It's going to be negative 1 over x squared, quantity squared. We're going to have a 1 over 4 there. Let's go ahead and take this thing to the next page. All right, so we have the surface area is equal to 2 pi times, okay, I'm going to rewrite this, the limit as t goes to infinity of 1 to the t, 1 over x, times 1 plus 1 over x to the 4th dx. So we just need to evaluate this thing. That sounds like annoying, though. Let's think about this for a second. Can we just determine whether it converges or diverges? Well, let's see. 1 plus 1 over x to the fourth. That's going to be 1 plus 1 over x to the fourth. That's going to be greater than 1. And the square root of 1 plus 1 over x to the fourth is going to be greater than 1. Because we're adding a positive number to 1 and square rooting it. That's greater than 1. So this thing is greater than 1. And 1 over x, we've already established. That thing diverges. That's like the idea 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, etc. We've already established that this diverges. So if I take something that's larger than 1 and multiply 1 over x, then that is going to absolutely diverge. This thing, I'm not even going to evaluate this thing. This thing totally diverges. Right? Maybe that sometimes it's enough to just determine that it diverges. Right? We have dealt with 1 over x now. Let's not worry about it. Right? The surface area diverges. Gabriel's horn has infinite surface area. Right, the next thing I want you to do, I want you to find the volume of Gabriel's horn. Right, volume, that's going to be pi from 1 to infinity of the radius squared. So 1 over x quantity squared dx, a little bit simpler. And wait a second, 1 over, Also, why did I do that? Sorry about that. This is volume, not for all. Pi times the limit as t goes to infinity of 1 to infinity of 1 over x squared dx. The antiderivative of 1 over x squared, that's negative 1 over x. So write that over here. We have pi times the limit as t goes to infinity of 1 over x, negative 1 over x, evaluated at 1 and t. And this should not be an infinity. This should be a t. I'm making a few mistakes here and there. I'm correcting myself. That's what's important. All right, so now when I evaluate this thing, I'm going to get pi times the limit as t goes to infinity of negative 1 over t minus negative 1 over 1 plus 1. Right, as t goes to infinity, this thing goes to 0. 1 stays 1, so I believe I'm going to get pi. Wait a second. Gabriel's horn has infinite surface area, meaning that if you give me a number, no matter how large, if I go out further enough in Gabriel's horn, if I go out further enough on this trumpet, I will eventually surpass that surface area that you gave me. Right, this will eventually have surface area greater than 1 billion units squared. But its volume is finite. Volume is equal to pi units cubed. It has infinite surface area, but the volume of this horn will never surpass pi units cubed. This object has infinite surface area, but finite volume, which means I can fill this trumpet with paint. If I go to the store, if I go to Home Depot and buy pi units cubed of paint and I pour it into this thing, it will fill it up. But I cannot paint it. I cannot paint the surface area of this horn. If I go to the store and I purchased pi units cubed of paint and I try to paint this thing, if I try to paint the outer surface of this, I will run out of paint. But if I pour the paint into the horn, so I can fill it with paint, but I can't paint it. And now that I've broken many of your brains, I'm going to stop there. Right? That is the beauty of mathematics. Sometimes we have confusing but profound solutions to problems. This is the difference between a mathematician and an engineer. Engineers, they say this problem is stupid and it makes no sense and it's not worth doing. The mathematician looks at this and says, wow, that's beautiful. There are objects that have finite volume and infinite surface area. And that contradiction is beautiful. But then again, I'll stop there. Let's look at what we did. Right here. We did a lot. We talked about two types of improper integrals. Type 1 was when we go off to infinity, or we go off to negative infinity, or we do both. An integral from negative infinity to infinity. Our bounds were infinite. Type 2 was when we had a discontinuity between our bounds. And what we did was we would split it up into two integrals and then take a limit as we go to that discontinuity point. We did a lot of examples along the way, and then we finished with Gabriel's horn, a solid with infinite surface area and finite volume. But yeah, improper integrals, and we can make these hard, believe me. One thing we didn't talk about now, and why it happens, why we do L'Hopital's rule right before improper integrals, because this might show up in some of our examples. In pretty much all of our examples, we had the limit of something minus something. And when you have infinity minus infinity, you have a battle. Bam! You have a battle. Right, so one thing we did not talk about in this video, but it might pop up in your studying, is L'Hopital's rule. Right? And then now that I got my one BAM for the video out of the way, I'm going to go ahead and close out here. I may or may not have just brought up L'Hopital's rule so that I could say BAM.